Welcome to Eternal Earth Stories, a place where time slows down and curiosity drifts like the tide. Tonight, let your thoughts rest as we look upward, not to the distant galaxies, but to the companion that has always been closest to us. The moon, Earth's silent guardian, has followed our nights since the very beginning of human memory. It is at once familiar and unknowable, constant yet ever-changing. Across centuries, across continents, across languages and beliefs, humanity has turned to its pale light for guidance, for wonder, and for stories that reach far deeper than science alone can measure. From the first moments when ancient people gathered around fires and lifted their eyes to the sky, the moon has been a mirror for imagination. Its phases carried meaning, its shape inspired myth, its glow softened fear of the dark. While the sun demanded worship with blazing heat, the moon whispered in subtler tones, its beauty quieter, its mystery more enduring. It was never just a piece of rock circling Earth. To those who came before us, it was a companion, a power, a clock, and at times even a god. In China, a story emerged thousands of years ago that has never faded. It tells of Chang'e, the goddess who lives upon the moon. There are many versions, but at the heart of them lies longing, sacrifice, and immortality. One of the most cherished tells of Hou, a great archer who saved the world by shooting down 9 of 10 suns that once scorched the earth. As a reward, he received an elixir of eternal light, but fate intervened. His wife, Chang'e, drank it herself, perhaps to protect it, perhaps out of destiny, and her body drifted upward until she could never return. She came to rest on the moon, where she remains, radiant yet distant, looking back at the world she left. Every mid-autumn festival, families in China honor her by gazing at the full moon and eating mooncakes, as if the shared ritual shortens the distance between Earth and her lonely light. The story of Chang'e is not only a tale of magic. It reflects something deeper. The way human beings use the moon to explore ideas of love, sacrifice, and eternity. For the people of ancient China, the moon was not lifeless. It held emotion, it embodied a character, and it connected the heavens to human hearts. Even today, as China sends spacecraft named after Chang'e to land on lunar soil, the myth is kept alive, blending past and future into a single thread. The Greeks, on the other side of the world, saw the moon not as a lonely exile, but as a goddess named Selene. She rode across the night sky in a chariot of silver, pulled by glowing horses. Her face was radiant, her crown gleamed, and she fell in love with a mortal shepherd named Endymion. To preserve him, she placed him in eternal sleep, so that his youth would never fade. For the Greeks, the moon embodied beauty and desire, but also the sadness of distance, for Selene could never fully share her world with the one she loved. The myth of Selene echoes with the same themes found in China's Changhua: love, longing, immortality, and the sky as a place where human feelings are reflected and magnified. Further west, the Islamic world gave the moon another profound meaning. The crescent became more than a phase of light. It was a symbol of guidance and faith. The Islamic calendar is lunar, each month beginning with the sighting of the new crescent. Ramadan, the holiest period of fasting and reflection, begins and ends with the moon's appearance. Mosques were built with crescents atop their domes, reminding the faithful that even in the vast desert night, God's presence can be traced in the cycle of light above. The moon became not only a measure of time, but also a visible sign of spiritual rhythm. These 3 examples, Chang'e, Selene, the crescent, are only fragments of a larger mosaic. The Mayans carved lunar glyphs into stone calendars. The Inuit told stories of brother sun and sister moon locked in eternal pursuit across the Arctic sky. In Africa, the moon was a lantern for travelers, and in many Native American traditions, it marked the timing of planting, harvesting, and gathering. Everywhere in every age, the moon entered the center of human imagination. It was never blank. It was filled with meaning. Part of this power lies in the moon's simple yet dramatic cycle. Every night it changes, growing and fading, with a rhythm so reliable that ancient people could trust it long before mechanical clocks were dreamed of. The phases gave structure to rituals, Hunters and farmers alike counted nights by its glow. Festivals of fertility gathered around full moons. When light stretched into the hours otherwise ruled by darkness, sailors launched journeys on bright nights, when tides were strongest, guided by the moon's silent hand upon the seas. The moon's waxing and waning was more than scenery. It was the pulse of early human life. Even in places without written records, archaeology shows how carefully the moon was tracked. At Stonehenge in England, giant stones stand aligned not only to the sun's solstices, but also to the complex cycles of the moon. In Ireland, passage tombs built more than 5,000 years ago were designed so that moonlight would fall into their chambers at specific times. Across the world, from the ruins of Babylon to petroglyphs in North America, marks on stone hint that the moon was humanity's first calendar, teaching people that time itself was a cycle, not a straight line. Navigation too depended on the moon. Polynesian voyagers, sailing vast distances across the Pacific, used the moon's rising and setting to steer between islands unseen for weeks. Bedouin traders crossing desert dunes followed both stars and the moon to maintain their course in endless sands. Before compasses, before GPS, the moon was a lantern in the sky, silent but constant, giving direction to anyone who learned to read its path. But while it guided and inspired, the moon also stirred deeper feelings: mystery, romance, and fear. Lovers compared their longing to its silver light. Poets wrote of its beauty reflected on rivers, and entire languages grew metaphors from its glow. Yet alongside wonder came unease. The full moon has long been associated with madness. The word lunatic itself comes from luna, Latin for moon. Folktales of werewolves, witches, and spirits often placed their power under its light. To the human mind, the moon was never neutral. It could enchant, it could guide, but it could also disturb. Science now tells us that the moon is a ball of rock, scarred by craters born from a collision billions of years ago. Yet for most of human history, its essence was emotional and symbolic. It was woven into songs, carved into temples, written into holy books. Even after telescopes showed its mountains and plains, people still gazed up and found in it reflections of themselves. When Galileo first turned his glass toward it in 1609, he discovered a landscape of valleys and shadows, but even then the sense of mystery only deepened. The moon became not less magical, but more complex. At once a physical place and an eternal symbol. It is important to understand this long story of imagination because it shows why humanity continues to reach for the moon today. When rockets roar upward and probes land on silent dust, it is not just science at work. It is memory, myth, and longing, stretching back through thousands of years. The moon has always been more than rock. It has been a guardian of dreams. And this guardian, though constant, has secrets still to share. As we move forward in our journey, from ancient legends to modern exploration, the moon will shift from a symbol in stories to a place of discoveries, shocking discoveries that remind us that even the most familiar companion in our sky can still surprise us. For most of the 20th century, the moon was not only a celestial body, but a stage on which two superpowers performed their rivalry. The United States and the Soviet Union, locked in the Cold War, transformed space into a theater where science, politics, and pride merged. Each launch was more than technology, it was a message. In the shadow of nuclear weapons and global tension, rockets became symbols of strength. The moon was the ultimate prize. Distant yet close enough to reach with imagination, funding, and the will to risk everything. In 1957, the Soviet Union shocked the world with Sputnik, the first artificial satellite. A sphere no larger than a beach ball, it emitted faint beeps as it circled the Earth. Yet those sounds carried weight far beyond their signal. They announced that humanity had entered a new era, the space age. The United States, startled and challenged, accelerated its own efforts. Only 4 years later, Yuri Gagarin became the first human to orbit Earth. His flight was brief but electrifying, proof that the Soviets had taken the lead. The American response was bold. In 1961, President John F. Kennedy stood before Congress and declared that the United States would land a man on the moon before the decade ended. At that moment, it was more promise than plan, but it set in motion the Apollo program. Billions of dollars, thousands of engineers, and years of intense work converged on a single goal: to step onto another world. The Soviet Union pursued its own lunar ambitions, testing rockets and probes, but it was the United States that achieved the decisive breakthrough. In July 1969, Neil Armstrong and Buzz Aldrin walked on the moon, leaving footprints in dust untouched for billions of years. The words, "one small step for man, one giant leap for mankind," echoed across the globe, not only as a triumph of technology, but also as a declaration of dominance. For the United States, Apollo was proof that open societies and free competition could outpace a rival system. Yet once the flag was planted and the goal achieved, the race slowed. Apollo missions continued until 1972, then ended. The Soviet lunar program faltered, its N-1 rockets failing spectacularly. For decades afterward, no humans set foot on the moon. Probes continued to orbit and land, but the age of daring crewed exploration gave way to satellites, space stations, and robotic craft. The dream of the moon lingered, but it seemed distant, overshadowed by other priorities. China, during those decades, was watching from afar. In the early Cold War, it had no ability to compete. Its economy was recovering from turmoil, its technology decades behind. But by the end of the 20th century, the situation had changed. Economic reforms had transformed China into a rising power. Cities expanded, industries flourished, and a new confidence began to shape national ambition. With prosperity came the question, should China also look upward? Should it claim its place among the stars? The answer was yes, but China's approach would not mimic the frantic rivalry of the 1960 SS. Instead, it would be careful, methodical, and deeply symbolic. Where the United States had drawn upon the language of freedom and competition, China reached for something older, something rooted in its own culture: the legend of Chang'e, the moon goddess. By naming its lunar program after her, China bound its modern science to ancient myth, making every mission more than a technical feat. It became a continuation of a story told for thousands of years. The first steps were modest but important. In 2003, China launched Shenzhou-5, sending its first astronaut, Yang Liwei, into space. He orbited Earth and returned safely, making China the third nation, after the Soviet Union and the United States, to achieve human spaceflight independently. This was not just a technological achievement. It was a statement that China had arrived as a spacefaring nation. From there, the Chang'e program unfolded like chapters in an epic. Chang'e-1, launched in 2007, was an orbiter that mapped the moon's surface with unprecedented precision for China's scientists. It was followed by Chang'e-2 in 2010, which refined those maps and tested new technologies. These missions may have seemed routine, but they built the foundation for bolder steps. Chang'e-3 in 2013 carried the Jade Rabbit rover, U2. It was China's first soft landing on the moon, the first by any nation since the Soviet Union in 1976. When U2 rolled down its ramp and began to explore, Chinese viewers felt pride in seeing their own machine move across lunar soil. It was not only a scientific instrument, but also a cultural symbol, echoing legends while proving China's engineering capability. The achievement that stunned the world came with Chang'e-4 in 2019. For the first time in history, a spacecraft landed on the far side of the moon. This hemisphere, forever hidden from Earth, had been observed only by orbiters. Its surface was rougher, more scarred by impacts, and its remoteness posed enormous challenges. Communication required a relay satellite, Keqiao, positioned beyond the moon to bounce signals back to Earth. Yet despite these obstacles, Chang'e-4 touched down safely, deploying another U2 rover to roam where no machine had gone before. Humanity had dreamed of the hidden side for centuries. China was the one to place a machine there. Why pursue such difficult missions? For China, the answer lies in more than science. It is about demonstrating independence, mastery, and patience. Where others rushed, China advances step by step, each mission building upon the last. The Chang'e program is not a sprint but a long journey, aligning with the nation's broader strategy of steady growth. It is a way to show the world that China does not need to imitate the past. It can create its own path. That path extends beyond exploration. The moon is not only a stage for politics or myth. It is also a frontier of resources and knowledge. By exploring the far side, by collecting samples, by building the capacity for return missions, China signals its intent to be more than a participant. It aims to be a leader in defining how humanity will use the moon in the future. Each mission is carefully timed to capture attention and to expand capability. Chang'e 5 in 2020 returned nearly 2 kilograms of lunar soil to Earth, the first new sample since the 1970s. Chang'e 6, launched later, targeted the far side for even more ambitious returns. These steps are not isolated. They form part of a roadmap that looks ahead to permanent bases, resource extraction, and eventually human presence. The choice of the name Chang'e underscores this dual purpose. To Chinese audiences, it evokes cultural pride, reminding them that their civilization's stories are as enduring as the moon itself. To international observers, it is a signal that China's space program is rooted in identity, not merely imitation. The moon, once the prize of superpower rivalry, has become a canvas on which China paints its own narrative. This determination reflects a broader truth. Space exploration is never only about science. It is also about meaning. For the United States, in the 1960s, Apollo was about proving strength in the Cold War. For the Soviet Union, it was about demonstrating socialist progress. For China today, it is about showing that it can rise on its own terms, blending myth and technology, patience and ambition. The story of China's leap to the moon is still unfolding. Its rovers move slowly across dusty plains, its orbiters quietly map craters, its scientists sift through grains of ancient soil. Yet behind these steady steps lies a vision that stretches far beyond national pride. It is about how humanity, guided by one of its oldest companions, continues to expand the circle of the known. As we leave behind the stories of myth and turn toward the reality of machines and discoveries, the moon begins to shift from symbol to laboratory, from goddess to ground beneath wheels and instruments. The path that began with legends now leads to questions of geology, resources, and mysteries hidden in shadow. And it is here, in the far side silence, that some of the most surprising revelations await. For as long as human beings have looked upward, one truth has remained. We only ever see half of the moon. The same face greets us each night, its scars and seas familiar like an old companion, while the other half is kept away, hidden forever from direct sight. It was once called the dark side, though it is no darker than the one we know. Sunlight washes across it in the same rhythm. What makes it dark is secrecy, a curtain drawn by the mechanics of motion. That secrecy comes from a quiet dance billions of years old. The moon rotates on its axis in perfect synchrony with its orbit around Earth, a condition called tidal locking. Long ago, when the moon was still young, Earth's gravity tugged at it relentlessly. Bit by bit, rotation slowed until one hemisphere faced us always. Now the moon's spin matches its journey around us, like a dancer circling the floor while never breaking eye contact. The balance feels eternal, and yet it hides half of an entire world. When spacecraft first looped around the moon in the mid-20th century, cameras revealed what eyes could not. The far side was astonishingly different. Where the near side is marked by broad volcanic plains, the Maria, dark seas of cooled lava. The hidden face is a rugged wilderness. Its crust is thicker, its surface older, its plains almost absent. Instead, there is a dense spread of craters, some stretching hundreds of kilometers, stacked and overlapping like scars upon scars. It looked like a place that had been forgotten by time, a record of impacts stretching back to the beginning of the solar system. Photographs only deepened curiosity. To stand on that hemisphere, to touch its rocks and measure its soil, promised answers. Why are the two sides so different? What stories lie locked in those ancient scars? But reaching it was a problem almost insurmountable. Any lander placed there would vanish into silence, cut off from Earth by thousands of kilometers of solid rock. Radio waves cannot slip through the moon. A craft on the far side would be like a diver at the bottom of an ocean without a line to the surface. That silence kept every mission of the 1960S and 1970S confined to the near side. The Soviets sent their Lunar probes, the Americans walked. During Apollo, later orbiters from many nations mapped the surface, but all landings and rovers touched down where Earth could still hear them. The far side remained a photographed mystery, never touched by wheels or instruments. China changed that in 2019. After years of careful preparation, a spacecraft named Chang'e 4 was launched, carrying both a lander and a rover. Its destination was bold, Von Karman Crater, a wide scar inside the South Pole Aitken Basin, one of the largest and oldest impact basins in the solar system. This was not only unexplored ground, it was a place that might expose the moon's deepest layers, rock from beneath the crust itself. But how could signals travel back? Months earlier, China had launched a relay satellite called Qiaqiao, meaning Magpie Bridge. It was placed in a special orbit beyond the moon, where it could see both the hidden side and Earth at once. Any message from the lander would bounce off Qiaqiao, travel across space, and return home. Without that silent bridge, the mission would have been blind. With it, the far side became reachable. On January 3, 2019, Chang'e 4 descended through lunar skies, its thrusters whispering against low gravity as it guided itself into Von Karman Crater. Through the Magpie Bridge, signals streamed home. Then came confirmation, landing successful. For the first time in human history, a machine had touched the far side. Ramps unfolded, and the rover U-22, the Jade Rabbit 2, rolled onto dust no human eye had ever seen directly. Its tracks marked the beginning of exploration in a place that for millennia had been hidden behind a curtain of silence. The moment was more than technical triumph. It was a key that unlocked questions scientists had asked for generations. Instruments aboard the lander and rover measured minerals, recorded radiation, and probed the soil. Cameras revealed the fractured rocks and crumpled landscape of the crater floor. Even a tiny biological experiment was carried, seeds sealed in a container with air, water, and soil. For a brief time, cotton seedlings sprouted under lunar light, the first living plants to grow on the moon before the harsh night froze them. A fragile green shoot, stretching upward in alien soil, carried symbolism far beyond its brief life. Science saw immediate value. By sampling the far side's terrain, researchers could compare it with the familiar near side. Why is the crust thicker? Why are Maria absent? Why does one hemisphere tell a story of volcanism and flooding, while the other is marked only by impacts? Clues gathered by U-22 offered the beginning of answers. Minerals in the soil hinted at deeper origins, perhaps from the mantle. Glassy beads formed in ancient impacts glistened under the rover's camera. Each detail was a fragment of the moon's memory, preserved where time had failed to erase it. Equally valuable was the far side's natural silence. On Earth, the atmosphere is filled with radio noise from technology, phones, satellites, radar. Even the near side of the moon reflects this interference. But the far side is shielded completely. No signal from Earth can reach it. For astronomers, it is the quietest place in the inner solar system. Here, a radio telescope could listen to the faint whispers of the early universe, signals from the first stars and galaxies, sounds erased everywhere else. Chang'e 4 began to test this environment, paving the way for instruments that may one day reveal cosmic history from a sanctuary of silence. For China, the achievement was layered with cultural meaning. The spacecraft carried the name of Chang'e, the goddess who rose to the moon. The rover bore the name of her companion, the Jade Rabbit, and the bridge of communication, Kietiao, echoed the folklore of magpies who formed a bridge across the heavens to reunite star-crossed lovers. Myth and technology met in the crater's dust, intertwining ancient story with modern science. The landing also carried political weight. No nation had attempted the far side. By succeeding, China did more than expand knowledge. It claimed a first that resonated around the world. While others had paused their lunar ambitions, China demonstrated that patience and determination could open doors left closed for half a century. From the crater floor, U-22 sent back images of shattered boulders, of soil broken into glassy fragments, of horizons where Earth never rises. To stand there, even through a camera's lens, is to feel isolation deeper than any desert. The near side offers a sky where Earth shines blue and bright. The far side offers only the void, a black dome unbroken by the familiar face of home. And yet, in that emptiness lies richness. The rocks are older, the craters untouched, the silence unbroken. Each measurement, each photograph, each grain of soil studied by Chang'e 4 adds to a growing picture of the moon's hidden history. And as scientists examined those first results, they soon realized that even greater surprises awaited, not only from the far side's landscape, but from the treasures carried back to Earth by later missions. In December 2020, after decades of silence, a new capsule streaked back through Earth's atmosphere, glowing as friction lit its skin against the night. It fell across the sky like a star that refused to vanish, parachutes blooming to slow its descent. When it landed on the snowy grasslands of Inner Mongolia, teams rushed forward in heavy coats, the bitter winter wind cutting across the open plain. Inside that small capsule was something humanity had not touched in more than 40 years, freshly gathered soil and rock from the moon. This was the Chang'e 5 mission, and though its journey had taken only weeks, it carried the weight of generations. Since the last Apollo astronauts lifted off the lunar surface in 1972, no new material had returned to Earth. For nearly half a century, scientists had relied only on old samples, orbiting observations, or meteorites that fell from the sky. Now, for the first time in living memory, researchers would open containers holding untouched fragments of the moon, sealed since the day they were scooped from its dust. The Chang'e 5 spacecraft was ambitious, a chain of modules working in harmony. It launched atop a long March 5 rocket, the heaviest in China's fleet, and carried 4 key parts: an orbiter, a lander, an ascent stage, and a re-entry capsule. Upon reaching lunar orbit, the lander detached and descended to Oceanus Procellarum, the ocean of storms, a vast plain on the near side. Using robotic arms and drills, it gathered around 2 kilograms of regolith, the loose soil that carpets the moon. Some was scraped from the surface, other portions drilled from as deep as 2 meters, reaching layers undisturbed by micrometeorites or radiation. Gathering samples was only half the challenge. Once sealed, the container had to be launched back into lunar orbit by the ascent stage, an astonishing feat of precision. It rendezvoused with the waiting orbiter, transferred its treasure, and then the orbiter carried the cargo home. The re-entry capsule endured fiery descent, then fell to the ground under parachutes, bringing its precious dust into human hands. The moment those containers were opened in clean laboratories, there was a hush of awe. Technicians in white suits lifted small glass tubes filled with gray powder, each grain a relic older than human civilization itself. The soil shimmered faintly, flecked with tiny beads of glass formed in ancient impacts. To the untrained eye, it was just dust. To scientists, it was a library written in minerals and isotopes, a storybook of lunar history waiting to be read. Why was this return so important? Apollo had already brought back over 380 kilograms of rocks. Did the world truly need 2 kilograms more? The answer lay not in quantity, but in location and timing. The Apollo samples came mostly from regions over 3 billion years old. They painted a picture of a moon that had been volcanically active in its youth, then cooled and hardened into silence. Chang'e 5, however, touched down in a younger volcanic plain, believed to be only 1.2 billion years old. If the dating held true, these rocks would show that the moon remained active far later than once believed. And indeed, that is what the first analyses revealed. The samples contained basalt, dark volcanic rock, formed when molten lava cooled on the surface. Radiometric dating, which measures the decay of isotopes within minerals, showed ages far younger than Apollo's finds. This meant that the moon's interior had retained heat longer, producing lava flows long after scientists thought its energy had faded. The moon, once thought geologically dead for billions of years, had flickered with life in the more recent past. This discovery rippled outward. If the moon had remained warm and active for so long, what did that say about the evolution of rocky worlds? Could small bodies preserve heat far longer than models suggested? Might Mars or other moons in the solar system also have had late episodes of activity? A simple handful of dust forced textbooks to bend, rewriting the timeline of lunar history. The samples also carried chemical signatures that hinted at deeper mysteries. Tiny crystals revealed how magma had cooled, providing clues to the composition of the mantle beneath the crust. Traces of water molecules, bound within minerals, suggested that the moon may not be as dry as once thought. Solar wind particles, implanted in the soil, showed how the sun's activity had changed across billions of years. Each fragment, no larger than a grain of sand, was a data point in stories stretching across cosmic time. In laboratories, researchers handled the material with reverence. They separated grains by size, peered through microscopes at shards of glass, dissolved specks in acid to measure isotopes. Some samples were distributed worldwide, shared with teams in Europe, the United States, and beyond, a gesture that echoed scientific cooperation even amid competition. Each group found its own surprises. Even the texture of the soil, its jagged, sharp-edged grains, told of a surface ground endlessly by impacts, unsoftened by weather, unshielded by atmosphere. For China, the return was more than science. It was a milestone in proving technological mastery. Only the United States and the Soviet Union had ever performed a lunar sample return. By succeeding, China placed itself in that rare company, showing it could not only reach the moon but also bring pieces of it home. The nation celebrated the success as a national triumph, while scientists quietly prepared for the next steps. What makes samples so powerful is that they can be studied again and again as technology improves. Apollo's rocks, collected half a century ago, are still yielding discoveries as new instruments probe their secrets. The same will be true of Chang'e 5. Stored in vacuum chambers, cataloged grain by grain, these samples will remain a resource for decades, perhaps centuries, as future scientists ask new questions we cannot yet imagine. The excitement in the laboratories was not just about confirming what was already suspected, it was about the potential for surprises. Already the discovery of relatively young basalt had forced a reconsideration of the moon's heat engine. What else might be hiding in these grains? Could new minerals be present, unseen until the right instruments reveal them? Could isotopes hold hints of processes never considered? Each possibility lent a quiet thrill to the work, even as the tasks themselves, sieving, labeling, measuring, were painstaking and slow. To the outside world, the return of 2 kilograms might seem small, but in science, weight is not measured in mass alone. It is measured in meaning. These samples were not just rock and dust. They were the first new voice of the moon in half a century, speaking in tones we had not heard before. And the voice was not finished. Within those containers, among the fine particles and shards of glass, there were hints of something even more extraordinary. An entirely new mineral, unlike any known on Earth, waiting to be recognized. Scientists would soon give it a name that tied myth and discovery together once again: Changesite Y. Inside the sealed containers of Chang'e 5, each grain of lunar dust was cataloged with care. Scientists spread them under microscopes, turning tiny crystals beneath beams of light, adjusting instruments so sensitive they could measure the structure of atoms. At first, what they saw seemed ordinary: Basalt fragments, glass beads, formed in ancient impacts, grains shaped by billions of years of bombardment. But then, among the fine powder, a shard revealed itself that did not match any entry in the catalog of known minerals. It was 2022 when the announcement came. After painstaking analysis, researchers confirmed the discovery of something completely new, a mineral never before identified on Earth. They named it Changesite. Why? Linking it to the Chang'e mission that had carried it home. With this naming, the moon had given humanity not just a sample of its surface, but a brand new piece of its identity. To understand why this was so extraordinary, it helps to think about what a mineral is. A mineral is a natural crystalline substance, defined by its specific chemical composition and the way its atoms are arranged in a repeating structure. On Earth, thousands of minerals exist, formed by heat, pressure, water, and chemistry. Most are familiar: quartz, feldspar, calcite. Others are rare, like diamonds or topaz. But every mineral is a kind of fingerprint, a record of the conditions under which it formed. Discovering a new mineral is like finding a new letter in the alphabet of nature, one that adds words we didn't know could be written. Changesite was tiny, less than a tenth the width of a human hair. It appeared as a single crystal among countless grains. To the naked eye, it would look like dust, but under the microscope, its structure revealed something unique. Using X-ray diffraction, a technique that shines beams through crystals to map their internal lattice, scientists saw a pattern no one had ever recorded. Its formula was determined as a phosphate mineral, rich in rare elements, crystallized in the volcanic basalts of Oceanus Procellarum. What made it remarkable was not only that it was new, but that it was lunar. The moon has been studied for decades. Apollo brought back hundreds of kilograms of rock, and the Soviet Lunar missions carried soil as well. To think that after so much analysis, a brand new mineral could still be waiting, unseen until Chinese scientists lifted it from dust, was a reminder of how much remains hidden in plain sight. The discovery was formally recognized by the International Mineralogical Association, the body that approves new entries into the official catalog of minerals. Changesite YA became the sixth new mineral identified from lunar samples, and the first discovered by China. Its naming was more than symbolism. It marked China's arrival not only as an explorer of the moon, but as a contributor to the fundamental science of what the moon is made of. But beyond national pride, the mineral carried geological significance. Its crystal structure spoke of the moon's volcanic past. Oceanus Procellarum, where Chang'e 5 landed, had been a region of lava flows more than 1 billion years ago. As molten rock cooled, different minerals crystallized out. Most were familiar basalts, but in rare conditions, elements combined in unusual ways, producing this delicate new lattice. Changesite, MPA, was a messenger from that cooling process, telling scientists that the moon's magmas were more chemically diverse than once believed. It also hinted at the role of rare elements in lunar geology. Some of the atoms locked inside the mineral, like yttrium, the Y in its name, are scarce on Earth and important for modern technology, from lasers to electronics. Finding them in a lunar crystal raised questions about how resources are distributed across the solar system. Was the moon once richer in certain elements than Earth? Could mining one day extract not only helium-3 for energy, but also rare minerals essential for technology? A crystal smaller than a hair had opened a conversation about the future of space industry. The surprise rippled outward. Around the world, scientists examined the published data, comparing it with what they knew of Apollo's samples. Many were startled that such a unique structure had gone unnoticed before. Was it because the mineral was absent in Apollo's collection? Or had it simply been overlooked? Either answer was intriguing. If absent, it suggested differences between the landing sites. Perhaps the region visited by Chang'e 5 had unique conditions. If overlooked, it showed that even decades of study are not enough to exhaust the secrets of lunar dust. Both possibilities underscored the importance of gathering new samples from diverse locations. Changesite YA also forced a reconsideration of how we think about the Moon's volcanic history. Previously, models suggested a relatively simple story. Early eruptions formed the Maria. Then the Moon cooled and hardened. But the mineral's presence pointed to a more complex chemical evolution, with magmas that could crystallize into unexpected forms. The Moon's interior, once thought monotonous, was in fact dynamic, with pockets of heat and chemistry that lasted billions of years. In the laboratory, the moment of discovery was less dramatic than the headlines suggested. No one gasped or shouted. Instead, there was the quiet hum of machines, the glow of monitors, the careful voice of a researcher noting a diffraction pattern that didn't match. Science often advances this way, not in sudden flashes, but in patient, repeated checks. Only after weeks of verification, cross-checking with other instruments, and peer review did the team allow themselves to celebrate. Yet within that quiet process was a deep thrill. The Moon had given them something entirely new. This thrill extended beyond geology. For the public, the idea that a new mineral had been found stirred imagination. It felt like proof that exploration still holds surprises, that even our closest neighbor can reveal something unprecedented. News outlets described it as a shocking discovery, a phrase that captured both the rarity and the wonder of adding a new building block to the universe's library. For students, it became a symbol of how curiosity, patience, and technology could uncover marvels from even the smallest grains of dust. The name itself carried resonance. By tying it to Chang'u, the moon goddess of legend, scientists connected the discovery to cultural memory. Just as the myth spoke of immortality and longing, the mineral spoke of endurance. Crystals forming in lava a billion years ago, resting untouched until a spacecraft reached down and carried them back. In that sense, science and story were not separate but intertwined, both ways of honoring the moon as more than rock. Yet perhaps the most profound part of Changesite versus Y was what it suggested about the future. If such surprises could still emerge from a mere 2 kilograms of soil, what might larger returns reveal? What unknown minerals, isotopes, or even resources might lie in untouched craters, waiting for exploration? The discovery was not an end, but a beginning, a reminder that every mission has the potential to reshape our understanding. And so the grain that shimmered under a microscope became more than a crystal. It became a symbol of how the moon, even in its silence, still speaks. From myths of goddesses to modern laboratories, from ancient lava flows to 21st century instruments, its story continues to unfold. And within that story lies not only beauty, but also practical potential. For among the moon's dust rests another element long whispered about, an isotope that could power humanity's future, helium-3. Among the grains of lunar dust brought home by Changra 5 was a clue not just about the moon's past, but about humanity's possible future. Mixed into the tiny particles of soil, bound up in the glassy beads formed by impacts and buried in the upper layers of regolith, was an element almost absent on Earth. It is called helium-3, and to some it represents nothing less than the dream of endless, clean energy. To understand why this is so, we first need to ask, what exactly is helium-3? Most people are familiar with helium as the gas that fills balloons and makes voices sound high-pitched when inhaled. That is ordinary helium, or helium-4, which has 2 protons and 2 neutrons in its atomic nucleus. Helium-3 is different. It has the same 2 protons but only 1 neutron. That missing particle gives it unusual properties. It is stable, non-radioactive, and extremely rare on Earth, present only in trace amounts, mostly created by the decay of tritium or escaping from the deep mantle. On the moon, however, it is far more common. The reason lies in the solar wind. For billions of years, streams of charged particles from the sun have bombarded the lunar surface. Earth's magnetic field shields our planet, deflecting much of this radiation. The moon has no such protection. Its soil has been exposed directly, absorbing atoms carried by the wind. Among them is helium-3. Over eons, it became implanted in the top few meters of regolith, accumulating slowly but steadily. Estimates suggest that millions of tons may be spread across the lunar surface, bound within dust that looks ordinary but contains a potential treasure. Why does it matter? Because helium-3 is a promising fuel for nuclear fusion, the process that powers the sun. Fusion occurs when light nuclei combine under immense pressure and heat, releasing enormous energy. On Earth, scientists have long sought to harness this reaction, hoping to create power plants that mimic the stars. Unlike nuclear fission, which splits heavy atoms and leaves behind long-lived radioactive waste, fusion is cleaner, producing little waste and no carbon emissions. The challenge is making it work. Most experimental reactors use a mixture of deuterium and tritium, isotopes of hydrogen. These can fuse at relatively achievable temperatures, but the reaction produces neutrons that damage reactor walls and create radioactive byproducts. Helium-3 offers a tantalizing alternative. When fused with deuterium, it produces helium and a proton-dominantly charged particles that can be captured directly as electricity. No harmful neutrons, no long-lived waste. The result is power both clean and abundant, the kind of energy source that could run civilizations for millennia. The catch is supply. On Earth, helium-3 is vanishingly rare, measured in kilograms. On the Moon, the potential is measured in millions of tons. If even a fraction could be mined and brought back, it could fuel humanity's future. Some scientists estimate that a single space shuttle cargo load of helium-3 could power the entire United States for a year. Numbers like these ignite imagination, stirring visions of a world where energy scarcity vanishes and fossil fuels become relics of the past. When Chinese scientists studied the Chang'e 5 samples, they confirmed what had long been suspected. The lunar soil is indeed rich in helium-3. Measuring isotopes in the grains, they found concentrations consistent with decades of predictions. It was not just theory, it was proof that the element is there, waiting in dust. Suddenly, the Moon's gray surface was not only a place of myth and science, but also of resources, a vault of fuel written about in science fiction, but increasingly discussed in real plans. China is not alone in this interest. The United States, Russia, India, and private companies have all spoken of helium-3 as a reason to return. But China has been especially vocal, with officials and scientists openly calling it a strategic objective. The Chang'e program is often described as step-by-step exploration, but within those steps lies an ambition: to prepare for the eventual mining of lunar resources, helium-3 foremost among them. Extracting it would be difficult. The element is not found in pockets or veins. It is dispersed through the soil at concentrations of only a few parts per billion. To collect it, vast amounts of regolith would need to be heated to hundreds of degrees, releasing the embedded atoms for capture. Imagine giant furnaces on the Moon, processing dust and storing the gas. The scale would be immense, but the potential rewards almost beyond calculation. This possibility has sparked what some call a new gold rush. But unlike gold, the prize is not jewelry or coins. It is the chance to solve the energy problem of civilization itself. If fusion reactors can be perfected, and that is still a major challenge, then helium-3 could provide fuel safer and more efficient than anything on Earth. For nations, this means power not only in electricity, but in influence. Whoever controls the supply could shape the balance of the 21st century and beyond. The dream of helium-3 has been around for decades, whispered in scientific conferences and painted in science fiction. What makes it more tangible now is evidence. The confirmation from real lunar soil, the demonstration that the resource exists in abundance. It is no longer only speculation. The samples in Beijing's laboratories are silent witnesses to a future where energy comes not from oil wells or uranium mines, but from dust gathered under alien skies. For the listener, it may seem almost too perfect, a clean, endless source of power, waiting just beyond our reach. And indeed, caution is warranted. Fusion itself remains an unsolved puzzle. Reactors have been built, plasma has been confined, but net energy gain, the point where the output exceeds the input, has not yet been achieved in a practical, sustained way. Helium-3 could make the process cleaner and more efficient, but only if the reactors are ready. For now, the dream remains partly in the future, a promise shimmering just out of reach. Yet the promise shapes behavior. It influences policies, budgets, and strategies. The presence of helium-3 adds urgency to lunar exploration. It explains why nations that once let the moon drift out of focus now speak of bases, landers, and permanent presence. It ties the quiet light in our sky to the machinery of geopolitics and economics. Think for a moment about what it means. The moon, once seen only as a beacon of romance or a frontier of science, is now also a potential mine. Its dust is not just history, it is commodity. Within those grains lie atoms that could change how cities glow, how industries run, how entire populations live. In this sense, the discoveries of Chang'e 5 are not only about what the moon was, but about what humanity may become. The excitement and the caution live side by side. In research halls, scientists speak with measured words, pointing out the technological hurdles. In newspapers and speeches, leaders speak more boldly, imagining colonies that dig and process regolith, pipelines of energy bridging worlds. Between these visions lies the long path of reality, filled with experiments, engineering, and patience. But the seed is planted. Helium-3 has become a symbol not only of possibility, but of destiny. And as we picture the furnaces and reactors of tomorrow, it is worth remembering that all this speculation comes from dust no wider than a grain of rice, carried across space in a capsule that landed on a frozen plain. Within those grains, helium-3 whispers of stars and of futures, of power drawn not from destruction, but from union, not from scarcity, but from abundance. The whispers are enough to stir imagination, but the soil carries more than fuel. It carries records of heat and cold, of lava and impacts, of secrets buried deep in crust and mantle. For helium-3 is only one thread in a larger tapestry. As the moon gives up its atoms, it also gives up its history, hidden in layers of rock that tell stories not only of itself, but of the entire solar system. And in those layers lie the next set of mysteries. Beneath the gray dust of the lunar surface lies a record written not in words, but in stone. The crust of the moon, layered by billions of years of impacts and eruptions, is like the pages of a book that has never been fully read. Every crater, every shard of basalt, every vein of mineral carries a fragment of its story. For centuries we thought this book was closed, its tale finished long ago. Yet the samples gathered by modern missions have revealed that some chapters are far younger than expected. The surprise came from volcanic activity. For decades, scientists believed the moon had cooled rapidly after its violent birth. Without a protective atmosphere and with a small size compared to Earth, it was thought to have lost its heat early. Volcanism, lava flowing from the interior to the surface, was assumed to have ended more than 3 billion years ago. That picture made sense. Most of the lunar marea, the dark plains visible from Earth, were dated to those ancient times. They looked like scars from a distant youth, frozen in place ever since. But when the Chang'e 5 samples were analyzed, their radiometric dating told a different story. Some of the volcanic basalts were only 1.2 billion years old, more than 2 billion years younger than Apollo's rocks. This meant the moon had remained geologically active far longer than anyone imagined. In planetary terms, 1.2 billion years is still old, but compared to a timeline of 4.5 billion, it is surprisingly recent. At that point, complex life was already flourishing on Earth. While forests grew and oceans teemed, the moon still flickered with heat, pushing lava up through fractures to paint fresh plains across its surface. This realization reshaped our view of the lunar interior. It suggested that the moon's mantle, the hot, slowly moving layer beneath its crust, had not gone entirely cold. Somehow, reservoirs of heat and magma persisted, long after models predicted they should have solidified. What kept that fire alive? Some researchers propose that radioactive elements, such as uranium and thorium, were concentrated in pockets, releasing heat through slow decay. Others suggest that tidal forces from Earth's gravity flexed the moon's interior, generating warmth through friction. Whatever the cause, the implication was profound. The moon was not a dead world as early as we thought. It carried a longer heartbeat, a hidden pulse within its crust. The basalt plains tell this story in quiet detail. Basalt is a volcanic rock, dark and fine-grained, formed when molten lava cools quickly. On the moon, these plains are vast, covering thousands of square kilometers. From Earth, they appear as dark spots, the seas once mistaken for water. Under a microscope, their crystals reveal the chemistry of the magma that created them, the balance of iron, magnesium, and silicon, the trace elements that whisper of temperature and pressure. By comparing these details across regions and ages, scientists can reconstruct the moon's volcanic history as if piecing together a film from scattered frames. What emerges is a complex picture. Some areas show evidence of huge ancient floods of lava, filling craters with molten rock until they became smooth plains. Others reveal smaller, more localized eruptions, suggesting that volcanic activity was not uniform but patchy, varying from place to place. The Changesite basalts added to this mosaic by showing that eruptions occurred much later in some regions than in others. This diversity suggests that the moon's interior was a dynamic, uneven system rather than a single cooling block. For scientists, this raised a tantalizing question. Could the moon still be active today? Most believe true volcanism ended around 1 billion years ago, but some surface features hint at younger activity. Small, smooth patches known as irregular mare patches look as though they might be only tens of millions of years old, mere moments in geological time. If confirmed, they would mean that the moon's crust shifted and bled lava far more recently than thought. No mission has yet sampled them directly, but they remain targets for future exploration. The importance of these findings stretches beyond lunar science. By studying the moon's thermal history, we learn how small, rocky worlds evolve. Why does Mars still show signs of ancient volcanism but appears dormant today? Why does Mercury, even smaller than the moon, display vast volcanic plains? And why has Earth, larger and more insulated, maintained active volcanism continuously? Each planet and moon is a variation on a theme, and the moon's story helps decode the broader pattern. It also offers a time capsule of the solar system itself. Earth's surface is constantly reshaped by erosion, plate tectonics, and vegetation. Mountains rise and crumble, seas shift, and life alters the landscape. Very little remains unchanged for billions of years. The moon, lacking these processes, preserves its history in place. Craters from ancient impacts remain sharp, lava plains lie undisturbed, and soil layers retain atoms implanted by solar wind. To read the lunar crust is to glimpse conditions that Earth has long erased. Consider, for example, the record of solar activity. The regolith contains particles blown from the sun across billions of years, trapped in glassy beads. By analyzing them, scientists can reconstruct how the sun's output has varied, how storms and radiation have changed over time. In this sense, the moon is not only a record of itself, but of the entire solar system's environment. Its soil is a diary written by the cosmos. Even the absence of certain features is meaningful. On Earth, volcanic activity is often linked to plate tectonics, the movement of giant slabs of crust across the mantle. The moon has no such system. Its volcanism must have been driven by different mechanisms: localized heating, radioactive decay, or the lingering aftermath of a giant impact that formed it. Understanding how volcanism worked without tectonics helps us imagine other planets and moons that lack Earth's churning plates. The secrets of the lunar crust also bridge science with imagination. To think of a world once alive with fire, now silent and cold, is to glimpse the fragility of planetary heat. If the moon once glowed with molten lakes and now lies frozen, what does that say of Earth's own future? One day our mantle too will cool, our volcanoes will fade, and the planet will fall silent. In the moon we see not only history but destiny, a reminder of the long arc of planetary life. Researchers continue to probe the basalts for every clue, tiny inclusions within crystals can trap information about pressure and gas content. Ratios of isotopes reveal the timing of eruptions with remarkable precision. Even the size and shape of crystals indicate how quickly magma cooled, whether it poured out in floods or seeped slowly. Each data point adds texture to the moon's biography, bringing the dry plains to life in our minds. And yet, despite all this progress, many mysteries remain. Why did volcanism persist so much longer in some regions than in others? Why did heat linger in isolated pockets? Could the moon still possess reservoirs of molten rock hidden deep beneath its crust? Instruments that measure moonquakes, tiny tremors caused by tidal forces, hint at structures beneath the surface that are not yet fully understood. Future missions may carry seismometers or heat probes to map these interiors more precisely, turning speculation into knowledge. For now, we rely on what the crust has chosen to reveal. Basalts that speak of ancient fire, craters that preserve violent impacts, soil that records the whispers of the sun. Each layer adds depth to our understanding, and each discovery seems to raise as many questions as it answers. The moon remains both familiar and mysterious, a world close enough to touch, yet still holding secrets in its stone. As these secrets unfold, they lead naturally to the realm of speculation. The same crust that records real volcanic activity also fuels myths and theories, ideas of hidden structures, artificial origins, or messages left in stone. Science provides the evidence, but imagination takes it further, weaving possibilities that stretch beyond data. From the basalt plains, our thoughts drift toward the mysteries that still hover around the moon, waiting in the twilight between fact and wonder. The moon is a world of rock and dust, its features mapped in exquisite detail, yet it has never lost its aura of strangeness. Perhaps that is inevitable. It hangs so close, luminous every night, and still feels unreachable for most of us. Even as spacecraft return images and samples, the moon seems to resist being reduced to mere geology. Facts are there, yes, but around them speculation grows like vines around stone. One of the most provocative ideas is the suggestion that the moon might not be what it seems. Some call this the artificial moon hypothesis, an unsettling thought that our nearest neighbor could have been built or placed with intent. The argument often begins with proportions. The moon is large compared to Earth, unusually so when set against the satellites of other planets. Its orbit and size produce a striking coincidence. In the sky, the moon and the sun appear almost exactly the same size. That alignment makes total solar eclipses possible, a phenomenon unique to our planet. For most astronomers, this is a fortunate accident of celestial mechanics. For others, it feels too precise, as though designed to be noticed. Then there is the story of the moon ringing. During Apollo missions, seismometers were deployed on the surface. When spent rocket stages were deliberately crashed into the ground to test them, the vibrations lasted longer than expected. Journalists at the time described the moon as having rung like a bell. To geologists, the effect came from fractured rock, transmitting sound differently than Earth's denser crust. To those inclined toward mystery, the phrase suggested hollowness, even the possibility of a constructed shell. Alongside structural speculation are the tales of visitors. Since the dawn of the space age, rumors have circulated about unusual lights seen near the lunar surface, objects rising, hovering, or vanishing. In the 1970s, fringe authors claimed Apollo astronauts had encountered structures, towers, domes, or machinery left by unknown hands. Photographs were circulated, often blurry or ambiguous, showing shadows that could be rocks or, to some eyes, walls and corridors. The power of such claims lies not in proof but in possibility. The moon's far side, unseen from Earth, was unknown until spacecraft mapped it. Even now, few people study the raw data themselves. That distance creates space for imagination to thrive. A crater rim can be recast as a fortification, a streak of light as a craft departing. Once the story is told, the image becomes difficult to see any other way. Photographs play a central role in these mysteries, taken in the rush of exploration. In that vast collection, there are always anomalies, unusual shadows, lens flares, or reflections. For most scientists, these are artifacts of light and optics, but in conspiracy circles, they are interpreted as glimpses of hidden structures, evidence supposedly scrubbed from public view. The simple fact that some Apollo photos were never released in real time, delayed by processing and cataloging, fueled suspicion. In an era defined by the Cold War, secrecy was common. Yet secrecy, no matter the reason, breeds imagination. Reports of lunar transient phenomena add another layer. For centuries, astronomers watching through telescopes described flashes, glows, or mists on the moon's surface, fleeting events that lasted minutes or even seconds. Some may have been impacts, tiny meteoroids striking with enough force to release a burst of gas. Others could have been visual illusions. Still, the records exist, scattered across centuries. They remind us that the moon is not as static as it appears, that now and then it flickers with activity. Why do these stories endure? Partly because the moon is personal. Unlike distant galaxies or even Mars, it is part of every human night. It feels familiar, yet out of reach. That tension between closeness and distance creates fertile ground for mystery. It is a blank canvas for culture to project upon, from ancient myths to modern UFO stories. And myths, in a sense, never fully die. The goddess Chang'e still floats in Chinese imagination, even as spacecraft bearing her name touch down. The crescent moon still crowns minarets and flags. Against that backdrop, it is no surprise that modern mysteries take root as easily as ancient ones. The moon has always been more than a sphere of rock. It has been a mirror of human imagination. Scientists, of course, remain cautious. No mineral sample has ever shown anything manufactured. No seismograph has hinted at hidden machinery. The chemistry of lunar dust matches the story of a natural origin, born from a giant impact with Earth, shaped by volcanism and bombardment. Each anomaly has an explanation within geology or optics, but science moves carefully, step by step. Speculation leaps. The leap is sometimes thrilling, sometimes misleading, but always engaging. That duality, measured science on one side, unbound mystery on the other, is what keeps the moon captivating. People do not gather late at night to tell stories about Mars's Olympus Mons. Though it is the tallest volcano in the solar system, they gather to tell stories about the moon. Because it looks down on them every evening, silent and suggestive. There is also the human desire for company. If the moon held structures or signs of intelligence, it would mean we are not alone, not just in the galaxy, but in our own sky. That possibility, however slim, is powerful. In a universe that often feels indifferent, it suggests connection, history, even purpose. To dismiss it entirely is to miss why it resonates. Still, science offers its own form of wonder. The moon's real secrets, hidden in basalts and isotopes, are no less strange than rumors of towers and bases, volcanoes that burned 1 billion years longer than expected, minerals never seen on Earth, helium locked in dust that could fuel future civilizations. These are marvels grounded in fact. They show that the moon is not empty or lifeless but layered with surprises. Speculation and science, then, are not enemies. They are partners in a way. Two voices responding to the same object. Speculation keeps curiosity alive, while science slowly turns some mysteries into knowledge. The Apollo era silenced some rumors but also birthed others. China's Chang'e missions have added new data, and with them, new questions. Each discovery seems to widen the field rather than close it. And as stories swirl about artificial origins, about UFOs, about classified images, attention gathers. Attention draws funding, funding builds missions. The very act of wondering, whether through myth or conspiracy, pushes humanity back toward the moon. In this sense, mystery itself is an engine of exploration. What began as whispers of hidden structures becomes, indirectly, blueprints for real bases. What started as questions about ringing vibrations becomes plans to drill deeper, to listen closer. Even the strangest theories play their part, keeping the moon in human focus. Which leads us back to the present. Around the world, nations are no longer content to watch the moon from afar. They are preparing to return, not simply to measure, but to stay. The same surface that fuels stories of secrets is also rich with resources, landing sites, and strategic value. Speculation may ask whether the moon was placed. Politics now asks who will place their flag there next. In the quiet of night, the moon appears serene, untouched by the struggles of Earth. Yet beneath its glow lies a stage for one of the most complex competitions of our century. What began as myth, then shifted into science, is now becoming something deeply political. The discoveries of recent decades, the unexpected volcanism, the new minerals, the potential fuel buried in dust, have transformed the moon from a symbol into a prize. It is no longer just a companion in the sky. It is becoming the next frontier of power, resources, and influence. The idea of a space race is not new. In the 1960s, the United States and the Soviet Union competed fiercely to demonstrate technological superiority. The race was fueled not only by curiosity, but by Cold War rivalry. Landing on the moon was a statement of power, a way to prove capability in rockets, in engineering, and national will. When Neil Armstrong stepped onto the lunar surface in 1969, it was not only a triumph of exploration, but also a political victory. That race ended with the collapse of the Soviet Union and the conclusion of the Apollo program. For decades, the moon was largely quiet, with only occasional robotic visitors. But the silence did not last. As new discoveries accumulated and as technology advanced, interest returned. The old race has given way to a new one, broader, more complex, and involving far more players. Today, the United States and China are the most prominent rivals. The US has launched the Artemis program, aiming to return astronauts to the lunar surface and eventually build a sustainable presence. Artemis is framed not only as science but as leadership, a signal that the US intends to guide international cooperation in space. Partners such as the European Space Agency, Japan, and Canada are already part of the effort, pooling resources and technology. China, meanwhile, has pursued its Chang'e program with determination, step by step. First orbiters, then landers, then rovers, then sample returns. Each success builds on the last. The stated goal is clear: to establish a long-term lunar research station jointly with Russia and to secure a role as a leading space power. For China, the moon is not just science. It is a matter of national pride and strategy, a way to show the world that it belongs at the front of technological progress. Other nations are joining as well. India has invested heavily in lunar exploration, with its Chandrayaan program achieving a soft landing at the South Pole in 2023. This was a landmark moment, making India only the fourth nation to land on the moon. For a country balancing development on Earth with ambition in space, the moon is a place to demonstrate capability, to inspire its population, and to stake a claim in the emerging order beyond Earth. Then there are the private companies. SpaceX, Blue Origin, and others are developing vehicles designed not just to reach orbit, but to carry cargo and people to the moon. Some firms speak openly of mining resources, establishing habitats, or building fuel depots. Unlike the state-driven programs of the past, this new race includes entrepreneurs who see the moon not only as exploration but as business. Contracts from NASA and partnerships with governments give them footholds, but their ambitions stretch further into visions of lunar industry. With so many actors, the question arises, who owns the moon? International law has attempted to answer. The Outer Space Treaty of 1967, signed by more than 100 nations, declares that no country can claim sovereignty over the moon or any celestial body. It is considered a global commons belonging to all humanity. Weapons of mass destruction are forbidden there, and activities must be peaceful. On paper, it sounds clear. Yet the treaty leaves gaps. While nations cannot claim the moon itself, the question of resources is less settled. If a country or company mines lunar soil and extracts helium-3 or water ice, do they own what they take? The United States has argued yes, passing national legislation that grants rights to private entities for resources they harvest. Luxembourg, the United Arab Emirates, and others have followed with similar law. Critics argue that this undermines the spirit of shared ownership, creating a system where wealthier nations can benefit disproportionately. The debate is not theoretical. Water ice at the lunar poles could provide drinking water, breathable oxygen, and hydrogen for fuel. Helium-3 could one day be used for fusion energy. Rare minerals might be mined for electronics. The value is immense, both scientifically and economically. Whoever controls access to these resources gains not only wealth, but strategic advantage. Bases near the poles, where sunlight is continuous and ice is plentiful, are already seen as prime real estate. This raises ethical questions. Should the moon be preserved as a site of heritage, like a cosmic park, or should it be developed, becoming a hub for industry? Some scientists worry that rushing into extraction could damage sites of immense geological importance, erasing records that cannot be replaced. Others argue that using lunar resources is essential for deeper exploration, reducing the need to launch everything from Earth. At the same time, there is the issue of security. Military uses of the moon are officially banned, but dual-use technology blurs the line. A communication satellite can also provide surveillance. A base for mining could double as a strategic outpost. The possibility of conflict is real, not because nations intend war, but because mistrust grows easily in uncharted territory. Space law is decades old and has not kept pace with technology or ambition. In this way, the moon becomes a mirror of earthly politics. Cooperation and rivalry intertwine. The Artemis Accords, a US-led framework for responsible exploration, have been signed by many countries but rejected by others, including China and Russia. Meanwhile, China and Russia announced plans for their own international lunar research station, inviting other nations to join. The result is a division, two visions of how humanity should approach the moon, each backed by alliances. And yet, competition is not only about division, it also drives progress. The first space race, though born of rivalry, gave us satellites, weather forecasting, global communications, and the first human steps on another world. The new race could yield similar advances: better rockets, new energy systems, new materials. It may be tense, but it is also productive, pulling humanity forward in ways peaceful cooperation alone might not. For those listening quietly at night, the political maneuvering might feel distant, but it is worth remembering that the moon is no longer abstract. Its dust is in laboratories, its images are in archives, its resources are being mapped and measured. Decisions about how to use it are being made now, by committees, by agencies, by companies. The serene face we see in the sky is tied to negotiations and strategies unfolding every day. The image of the moon as a new frontier is both inspiring and sobering. It recalls the great frontiers of Earth: oceans crossed, continents colonized, poles reached. Those ventures brought discovery, but also conflict, exploitation, and uneven benefit. The challenge for the 21st century is to avoid repeating those mistakes on a larger, cosmic scale. Can humanity treat the moon as a shared inheritance, or will it become another arena of competition and inequality? This question lingers in every policy document, every press release about new missions. It lingers in the minds of those planning the first permanent bases, the first extraction sites, the first partnerships between public and private ventures. The moon is no longer distant myth or sterile geology. It is a living part of geopolitics, and its future is entwined with ours. And from this point, reflection becomes unavoidable. The rivalry for the moon is not just about resources or science. It is about identity, who we are as a species and how we choose to extend ourselves beyond Earth. The next step in this story is not about machines or minerals, but about meaning. As nations draw lines in lunar dust, philosophers and dreamers ask what it says about humanity's path. That is where our journey now turns. The moon has always been there, steady and patient, even before anyone knew what it was. For most of human history, people saw it only as light in the darkness. Sometimes a companion, sometimes an omen, always something greater than themselves. Now, after centuries of myth, decades of exploration, and years of new discoveries, we know it as a world of stone and dust. And yet, in knowing more, it has not become less. If anything, its mystery has deepened. Each mission, each sample, each photograph adds another layer to our understanding. Volcanic basalts whisper of a fire that once lingered longer than we imagined. Minerals never seen on Earth remind us that the universe still has surprises. Resources buried in the regolith suggest futures powered by what now feels like imagination. And above all, the moon reflects us, our curiosity, our ambition, our endless desire to reach further than the horizon. Standing back from the details, it becomes clear that the moon is more than geology. It is a mirror of humanity itself. When we look at it, we see not only craters and shadows, but the reflection of our own story, the myths we tell, the questions we ask, the futures we dream. Its face has been a stage for gods and lovers, for scientists and astronauts, for conspiracies and discoveries. In its silence, we project our own voices. What do these new discoveries mean in a deeper sense? They tell us that the universe is not static. Even the moon, long thought to be cold and still, held on to warmth far longer than expected. Its crust records activity billions of years apart, yet present in the same stone. It reminds us that time is vast, and that endings are rarely as final as they appear. If the moon can still surprise us after so many centuries of watching, perhaps the universe holds countless other surprises still unseen. In this way, the moon becomes more than a destination. It is a lesson in humility. For every answer we find, more questions appear. We thought volcanism had ended billions of years ago, yet samples said otherwise. We thought its surface was inert, yet tiny flashes suggest activity. We thought we had cataloged its minerals, yet new crystals emerged. Each time, the moon reminds us that certainty is fragile and curiosity is necessary. This humility connects directly to ambition, because the very fact that the moon holds secrets pushes us to return. Nations plan colonies, research stations, permanent outposts where people might live for weeks, then months, perhaps even years. These bases will not be myth, but reality. Concrete modules rising from dust, antennas stretching into darkness, lights glowing where for billions of years there was only night. The moon may become not just a place we visit, but a place we inhabit. Imagine a settlement near the South Pole, sunlight brushing the horizon for nearly the entire lunar year. Solar panels stretch outward, catching steady energy. Nearby, icy soil is melted, producing water to drink and oxygen to breathe. Scientists step out of airlocks in bulky suits, collecting samples, planting instruments, watching Earth rise above the horizon like a distant lantern. This is no longer science fiction. Plans are being drawn, funding allocated, rockets tested. Within decades, these images could be real. Living on the moon will not be easy. Its surface is harsh. Temperatures swing hundreds of degrees. Radiation streams unhindered by atmosphere. Dust clings to everything it touches. But humanity has a long record of turning hostile places into homes. Deserts, polar ice, even orbiting stations. Each has taught us how to adapt. The moon is simply the next step. And in taking that step, something profound happens. The moon stops being out there and becomes part of our living space. It will no longer be just a light in the night sky, but a neighbor we can visit, a partner in survival, even a second home. That transformation changes not only technology, but imagination. Children born into such a future will look at the moon and know people live there. The line between myth and memory will blur, but beyond survival and settlement there is symbolism. To build on the moon is to claim we are more than Earth-bound. It is to say that exploration is part of who we are. Each base, each colony, will carry flags and languages, but also something larger. The idea that humanity belongs to the cosmos, as much as to the Earth. Yet the moon is not simply an opportunity, it is also a responsibility. To mine its resources, to construct habitats, to alter its landscape, these choices define what kind of species we are. Do we exploit recklessly, repeating mistakes made on Earth? Or do we step carefully, balancing use with preservation, acknowledging the moon not as empty land, but as a partner in history? These questions, philosophical as much as practical, will shape our path. The moon's light reflected from the sun has always been symbolic of reflection itself. Under it, poets wrote, lovers walked, armies marched, astronomers dreamed. Now, as we prepare to reshape its surface, that reflection turns back on us more clearly than ever. The moon asks, what will you become? It is worth imagining a night decades from now. You look up, and there, beside the familiar craters, are faint points of light. Not stars, but human lights on the moon. Settlements glowing softly, signals beaming toward Earth, evidence that the silent guardian is now inhabited. The mystery remains, but it has changed form. It is no longer a mystery of distance, but of what humanity will do next. And perhaps that is the most profound reflection. The moon is both ancient and new, constant and changing, silent and filled with stories. It has been a goddess, a guide, a puzzle, and now, perhaps, a home. In its glow, we see the best and worst of ourselves. The capacity for myth, the hunger for knowledge, the drive for power, the hope for connection. As these thoughts settle, the moon itself continues unchanged, drifting in orbit, casting its pale light across seas and forests, deserts and cities. Its rhythm is steady, its silence complete. Yet to those who watch, it is never the same. With each discovery, each plan, each dream, it grows richer in meaning. And so we arrive not at an ending, but at a pause. A moment to breathe, to imagine, to let the moon's light wash over us, as it has for countless generations. Its surface holds stories written in stone. Its glow carries reflections written in us. Under that light, curiosity softens into wonder, and wonder drifts into rest. The moon remains above, steady and silent, while thought slow and sleep gently arrives.